Hello again, we're on to sheet 4 of ME4111. So this will be question 1 on tutorial sheet 4. If we look at it here, what we have is a truss that has a number of forces acting on it. And we're asked to determine the equivalent force coupled system acting at point A. So point A is over here at the wall. We've got these 4 forces acting on it. We're given some geometric info on it so we can figure out the directions. We want to replace these 4 forces with a single force acting at point A, and also taking into account the turning effect due to the moment due to those forces. Then we're asked to make any conclusion based on the equivalence of the system at any point. So if you wanted to extend from point A to anywhere else, is there anything we can conclude from our result in that respect? Okay, so we look at the solution that we have, and the first thing I've done is I've broken each one of the forces into their components. So I've labeled F here, just mark it for you. So this force F and minus F I've done here. And then if we go to the 5 kilonewton force, we call that F2, and this one here is minus F2. So I've broken each of those forces into their components. So we got 6 cos 30 I hat plus 6 sin 30 j hat. So again, plus x direction plus y direction. Minus that because it's minus 6 cos 30 I hat minus 6 sin 30 j hat. So that's that one going down there. And the other one then I've broken into the components. So minus 3 I hat plus 4 j hat. So again, that's easy. It's being broken down by the triangle or the slope that is given there. And here we got plus I hat and minus j hat on that one. So 3 I hat minus j hat, minus 4 j hat in kilonewtons. Okay, so looking at those forces and just by inspection, essentially what I've done is I've broken the 4 forces into 8 forces. So I've replaced them now with forces acting in the I hat direction or the j hat directions. And essentially what I have now are a series of couples. So there's 2 couples. The first is due to this force F, so equal and opposite. Different lines of action, separated a distance apart. And I have the 5 kilonewton here. So all of these force kind of systems, you keep an eye out for couples. And as you recall from the lectures, identifying things as couples is extremely powerful because it allows you to move them to any location whatsoever we're going to take in a moment. So we'll come back to that later on. Right, so step 1 is that the translational effects, and what we have is that all the forces cancel because we've got 2 sets of couples. Okay, so this force cancels with that, and that force cancels. Okay, if you didn't spot that, what you would do is you would move each of these forces down to point A and sum them all up at point A. Okay, so if we do that, we get the sum of the forces equal to 0. So that's very straightforward. The second step then is to look at the rotational effects, and now we're taking moments. Okay, so what I'm doing is I'm taking a moment. If I didn't spot there were couples, I'd be doing it due to each component of the force. So I'd have 8 moments to take, and I'd be taking it from the line of action of the force to where the point A is. Now, because I've spotted that these are couples, I'm going to work out the value of the couples and then just relocate them to point A. So for the first one, I'm just taking the x component. So again, I'll just mark that out. So I'm taking this component here, that component here. So that is giving me a rotation that goes in that direction. Okay, so that's where I'm getting this minus from. So I've got the magnitude of one of the forces. So 6 cosine 30 is the force. And the separation then is 1 meter. Okay, and my minus then is coming from the direction. The vertical component then, so if I look at this and this component, you can see that that's causing a rotation to cause like that, which is clockwise. So that's why I have a plus here. Okay, so the plus has got nothing to do with the direction of the forces. It's due to the direction of rotation. So 6 sine 30 is my magnitude of one of the forces, and I have 3 as my distance, which is the distance between the lines of action. Okay, the spacing between them. Okay. Then I come to the next set of forces, which is, I'll stick with the red. I've got this one here, 5 kilonewtons. Sorry, the 3 kilonewtons, 3 kilonewtons. And then I have the 4 acting up there as well. Okay, so if I take the, oh, I have this force, and I also have him out and just move him over here. Okay, so that's where I'm getting the 3 from. Again, that is causing a rotation in the direction that you'll be able to figure out the directions from. So don't ever assign the directions based on the direction of the force. Look at the directions of the rotation. So again, these are all, it's a 2D problem, so they're all in the k hat direction. So I've got minus 6 cos 30 times 1 plus 6 sine 30 times 3 plus 3 times 1 minus 4 times 3. And again, those directions are coming from the directions of the rotations. Okay, so that gives me then the 5.2 kilonewtons as my answer. Okay, so my overall answer then is that the force coupled system is 0 newtons and a rotation of minus 5.2 kilonewtons. Again, I've indicated here as a clockwise rotation of 5.2 kilonewtons. Now, at the very, very start, we were asked, what can we conclude regarding the equivalence of the system at any point? Well, what we have is just a pure rotation that is taking place. Okay, so it is purely a couple. And that means that, you know, if we take point A, we take a point here, point B, any location whatsoever, the equivalent force coupled system is simply 5.2 kilonewtons.